Hi, welcome to Intro to Epidemiology Part 2.
You're not sure.
Okay,
Can you duplicate?
okay. Okay, so a recap what we covered. We covered about definition, scope, and history of epidemiology. We covered role of epidemiology in public health. We covered a little bit of the key measures of disease frequency and association. So let's go back. All this you have the slides, I think. If not, you can look for me. So we cover incidents. Remember, we call incidents new cases. Okay, two ends, so new cases. Prevalence only one end. So this is for present. How many does it have in the couple in the population now? Okay, so there are two parts: point prevalence at one specific point and one period prevalence. If it's not spoken, they usually refer to point prevalence. Yeah, but actually most of the time what they mention is about period. Yeah. For example, when you talk about prevalence or diabetes, what they're referring to is actually prevalence of diabetes at a certain point. So when you do this, as I mentioned 2 weeks ago, not sure if I remember, you're supposed to take the start population and the end population and then come up with the mid population. But this is more for countries where the population numbers can vary a lot from the start of the year and the end of the year. But for countries where it's quite stable, you can just take the average or the midpoint or the last year. Okay, but all these are the details. So basically, it's just referring to current cases. So you can think of it, I think Ernest mentioned, is the stock, and then the new cases is the flow into the system. There's a bit of system dynamics. We also covered this, remember, mortality rate. So when I talk about mortality rate, a lot of times it's crude. Crude is unadjusted. So a lot of times we talk about mortality rate, we need to look at age adjustment. Why age adjustment? Because it's more likely that the older you are, the higher your death rate. So it's not very fair to compare two populations. Imagine you compare a population in a younger group versus an older group and compare the mortality rate or death rate in both. Then you realize that the one with older population will have a higher crude mortality rate. That's why when you compare between years, for example, in Singapore, we always look at age-adjusted mortality rate to account for population aging. Okay, but the fact is that the crude mortality rate is the real rate, the rate that you see. When you do the adjustment, you are trying to isolate away the effect of age on it, and therefore it's a much more fair comparison. So you're asking a what if question. For example, if there is no aging, for example, look at 2000 and 2020. In year 2000, if there's no aging, in 2020, what is the death rate if there was no aging? Yes, please.
Yeah, I suppose in the case of our registries like cancer registry and all these things, published by MOH, they always publish the so-called normalized or age-adjusted rate so that we can compare the mortality rate of say cancer or whatever across multiple years. So they'll publish the crude rate and the adjusted rate.
Yes.
And the population is always normalized to a standardized population, SEGI or whatever.
Yeah, so they actually use a standardized population. So there are two ways of standardization. One is called direct, one is called indirect. I'm not sure we'll cover it today, but we'll cover this. Okay, so any questions before we move on? I think we stop here, I'm not wrong. Mortality rate. Okay. Oh, actually, okay. So this is called relative risk. Okay, relative risk refers to the ratio of the incidence of those in the exposed among those that is unexposed. So when you talk about this, it's usually talking about cohort study. So cohort study is very simple. You know cohort, right? Cohort is like, for example, a cohort of patients from year 1 and you follow that up for 10 years. So this cohort over time, this is supposedly to be a better form of observational study, because at a point of time when they enter the study, they are disease-free. They are disease-free. So for example, one group are smokers, no lung cancer. One group, non-smoker, no lung cancer. So this is one cohort of non-cancer patient. Some smoke, some do not smoke. Then you follow that up for 10 years. Now I found that the ones that smoke, let's assume there are 1,000 in each group. The 1,000 group, 100 have lung cancer, the smoking group. The non-smoking group, 10 has lung cancer. Okay, then you compare the incidence 100 over 10, so it's 10. So the relative risk of smoking that cause lung cancer is? Can you repeat myself? Okay, so you have two cohort of patient, 1,000, 1,000. Okay, so denominator is the same, so just ignore
10
denominator.
10 times.
So the incidence, the new cases of lung cancer in the smoking group is 100. The number of new cases of smokers of lung cancer in the non-smoking group is 10. So just take simply 100 divided by 10, so that's 10. So that is the intuitive idea of 10 times the risk. So if you smoke, your risk is 10 times. Doesn't mean you definitely get lung cancer. But if you don't smoke, again, it doesn't mean you won't definitely have lung cancer. Just that your risk compared to a smoker is 10 times less. Okay, yes, please.
This is not causality, but it's still correlation.
This is not causality, but it's stronger because at a point of time, both sides didn't have lung cancer. So you cannot say that because I have lung cancer, I smoke. Yeah, because at the start, none of them have lung cancer.
Yeah.
So that you cannot argue the other reverse causality. You cannot say that lung cancer is associated with smoking because at the start, none of them have lung cancer. Okay, I'm repeating myself already. Yeah. So this is a cohort study. So it's an observation study. You don't do anything. You just observe them. Actually, you do something. You recall them sometimes. You give them a call. Imagine you give them a call. Each time you call, if you call, they ask them whether they got lung cancer. Some people, if you're a smoker, if people every year call you, say you got lung cancer or not. This is actually an intervention. Think about it. Right? Yeah. Then you ask yourself, why are you asking me whether I got lung cancer or not? Then go and Google, oh, smoking associated with lung cancer. Then you stop smoking. So you actually have an intervention. Okay. But that's by the spirit, let's assume there's no intervention. It's just pure observation. So this is something like what we learn in physics, right? The observer can affect the
Quantum physics.
yes. So when the fact that you observe the movement, or the position can affect the momentum. Okay, anyway, beside the point already. The velocity. Yeah. Okay, so the observer does affect. Wow, Mary is taking notes. You have the slide, don't worry. So just remember, this is a simple idea.
Yes,
Okay. Yes. Oh, sorry.
No, not question.
Okay, so this is a
Actually,
course.
this is what the newspapers will always pick up, right? You have you will say that having some smoking is 10 times the risk of a non-smokers. So they use this. But having said that, of course the absolute risk could be very low. So even it's 10 times, it's 20 times, it may not be higher.
Okay, fair enough.
Not for lung cancer, of course, not for lung.
If I'm not wrong, right? Who studied epidemiology? If I'm not wrong, right, smoking is 50 times. That's why the quantity is also very high. That's why the association or your causation is higher. If it's only 2 times the relative risk, the strength of association is weaker, so causality is less. But it's 50 times. Then by chance, quite unlikely is that. So that's why the causality is there. Later I'll cover what are the 7 factors of causality. Hughes criteria of causality will be covered. Okay. So the other thing to remember is there's prospective and retrospective. Okay, prospective is straightforward. You recruit the patients or the people and you just follow them up. Okay. And then retrospective is you already have a cohort of patients and look back. Okay. What's the problem with a retrospective study?
You don't have immediate result.
No, actually, retrospective, you have the immediate result.
Sorry?
You have the immediate result. Retrospective study.
Oh no. What you mean?
What's the problem with prospective is better because you recruit them and you follow them up. But for retrospective, what is one of the big problem with retrospective study? Yes, possible. Yeah, you may choose those as selection bias. And one important thing is this thing called the immortality bias. Because when you do retrospective, right, and they are still alive now, then they cannot have died during the study period. So when you do retrospective study, you must make sure that you ignore the fact they die. A lot of people like to say, okay, let's take a retrospective cohort and they must survive until today. If you do that, right, then they have no chance to die. Then your study is very biased. So it's some sort of a selection bias. So make sure when you do retrospective study, right, just don't look at whether they died. Just take, okay, I want to take smokers. Then I take these smokers. or yeah. Otherwise, you do a retrospective study and you found that you do a retrospective study of 20 years for smokers and found that the lung cancer rate is very low. You know why? Because you're picking up the survivor. So they have survived for 20 years. Those who didn't pick up, okay, died in the 20 years. So they have very high risk of lung cancer. But those that if you just take back 20 years and the criteria is they must be alive today. So they are survivor. They may actually have a paradoxical lower risk of lung cancer compared to the other group. But of course, this works both ways. Even in the non-smoking group can have the same problem as well. So in actual fact, we need to be very careful about selection. But actually, to keep the long story short, prospective study is a bit stronger than retrospective. But in our case, in our department, we always do retrospective study. Why? Because you can do back 10 years, right? Then you can see the effect, right? Imagine you do a prospective study today, 2024, and you tell Prof. John, the result will be out in 10 years' time. Not funny, right? Yeah. So you can't, right? But on the other hand, if you say, I want to do a retrospective study for 10 years, you can go to CDMS or whichever database you have, look back 10 years, and then you can find whether is there any association with this and that. So that is the strength of doing a retrospective study versus a prospective study. But there's a lot of prospective study. Anyone know of any of the prospective study done in Singapore? Very simple one. I give a clue. There's Singapore and there's race. You know how you heard of the studies? Can you just Google? It's called a Singapore Chinese study. And if there's a Singapore Chinese study, Singapore Chinese cohort study, and there's also a Singapore Malay cohort study, and there's also a Singapore Indian study. So they actually combine a lot of studies.
Is it
So
Malay
yeah,
and
so,
Indian?
so okay, you want to ask a story? Very interesting. Okay, you see Mimi. Okay, the story was there's this cancer epidemiologist. I think she's still alive. I hope so. Okay, her name is Mimi Yi. No, that's not Mimi Yi. Okay, never forget her name already. So she's a US epidemiologist. So we did the Singapore Chinese study, and she handed over this study to this lady called Ko Woon Hui. Yeah, so she has this study. So if anybody want to do a PhD under Ko Woon Hui, she's good because she has this Singapore Chinese cohort study. As I mentioned, every few years they will ask them back and check on their things to see what happened. So this is a study that found that women's non-smoker have higher risk of getting, have quite a significant risk of getting lung cancer. Yeah, that's a Singapore Chinese cohort study. You can Google about it. So whatever I tell you today is all useful information that you can search. Okay, move on. You know, I cannot finish. Yes, you ask another question.
I mean, in terms of you talk about database studies, but although it is a collected data, but perhaps we can also create design in such a way that it becomes like look forward. I mean, it has to be careful. I mean, one thing that we, I mean, in one of our studies that, echoing what Dr. Gary said, when we look at patients who died or life expectancy of diabetes patients, then for instance, once upon a time, we go and run those with, look at the so-called the age that they die, diabetes and non-diabetes, and you find that those with diabetes died later than those with non-diabetes. So apparently it doesn't make sense in terms of medical. And if you think about it deeper, it is not a data crunching issue, but it's because of the selection bias issues, the way that you do the design. So I mean, in short, we are saying is that those with diabetes, you have to survive long enough in order to get diabetes. So therefore, there's some sort of selection bias. But if we have, I think at that point in time, Cheney did another way of looking at data. So at certain point of age whereby all the population or the selected cohort has no diabetes, from then onwards, we so-called track them forward. And then we track those with diabetes and those without diabetes. And indeed, for this kind of cohort, we show that those with diabetes will die earlier. Right?
So for this study, there's also competing risks. So if you don't die of diabetes, you may die of other things at a younger age. So you must also be very careful with this. Yeah, for example, if you look at the study of life expectancy of Alzheimer's disease, for example, you find that a lot of them are very old. And then you come up with the idea that Alzheimer's disease give you long life. But maybe it's not true. It's because those who didn't have a chance to actually experience the Alzheimer. This is an example. So be very careful with analysis. So whenever analysis, think through and then check again to see whether there's any other explanation for it. Okay, one thing I forgot to tell you about retrospective study is that retrospective study, the data is already collected. So there's no way you can collect it. Even you can collect it and call the patient out, there will also be recall bias. On the other hand, prospective study, you design the study properly. If you miss out certain things, you can come out and give them more information to collect more information. So that's another strength of prospective study versus retrospective study. Okay, odds ratio. Okay, this is a bit different. This is for case control study. Okay, first thing is what's different between case control and cohort study? Okay, some you must have heard of this. So basic case control study is people with the disease. So there are two approaches to doing things. So first approach is nobody has the disease. Somebody got risk factor. Then you follow them up. But for rare diseases or disease that it takes very, very long, it's a very inefficient way to doing things.
Yeah.
So they cannot this much, they call it, I don't call it cheating. I just call it a different way of looking at it. We look compare people with the cancer versus people who are similar but no cancer. So for example, I look at a group of people with lung cancer, and then for the same age, gender, blah, 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 find another group with no lung cancer. Then I go and track back, what are the differences? So the lung cancer group say, nothing much. I just remember you was young and smoke. Okay, then the other group with no lung cancer, anything, nothing much. Oh, I did try one cigarette. Then I stopped. I didn't like it. Then you find that one group smoked 10 years. The other group only tried one cigarette. Then you kind of speculate that it could be because lung cancer is caused by smoking. Because the group with lung cancer versus a group that's very related to the lung cancer group but don't have lung cancer, has only this difference. So that's how I came out with this odds ratio. It's very common for conditions that are rare diseases. They can use this design. Okay, so this is observational study to compare individual with the disease, the cases, with those without the diseases. But the selection criteria is very important again, because your control must be very similar to the cases. Otherwise, it's an unfair comparison. Yeah, so selection of controls is important. Okay, so this is case control study. Don't worry, we'll go in depth. Today is an intro class. Okay, so the intro class will go through certain things. Just try to remember it, and then we'll go in depth into the difference between cohort case control studies. Okay. Okay. Any question? Move on. Okay. Next, data collection. So straightforward. I think you're expert in surveys. Okay, so surveys are two types. Okay, one is those that are more structured questionnaire. These are more numerical data, and there are some that are more open-ended. Okay, why do people don't like open-ended questionnaires or open-ended surveys?
Takes longer to answer.
Okay, one thing is easy for people to choose 1, 2, 3, 4, 5, right? If I need to write, imagine you ask, can you write in 3 sentences? Every question must write in 3 sentences. It's an essay question, right? Very, very scary. Okay, first, you may have not a good response. And number 2 is after people write, right, you need to do text mining. Okay. Okay. In the past, they have different methods. Now you can use a large language model to do sentiment analysis, text mining. So this is something I actually explored. So you can also look at, okay, the easiest way in the past, what they do is look at words people use. So they compare words that are positive, that's sentiment analysis, words that are neutral, words that are negative. Okay, but one of the biggest problem with this, which I did when I study, is that sarcasm is always missed out in sentiment analysis. So of those very verbosity, some of the words are too things they can miss out. And people when they write irony also, they will say, this is the best restaurant I ever had. I'll never come again. So people see the best, they thought it's positive. Yeah, and then never come again, negative. So they thought it was neutral. But I ask you, is this neutral? This is the best restaurant I came. I'll never come again. So the text mining will say this is neutral because one positive, one negative. But most of us will say this is negative because it was being ironic. Yeah, people like do that. Yeah, because some of the, you know why people do that? Because some of the filtering things, right? They'll filter off negative comments. So that's a lot of websites you see, hey, all positive comments. How oh, so good is it? Then you go, oh shit, the food sucks. Because all the negative things are filtered out. So to counteract this, they start to use irony and funny things to say that this is the best restaurant I come across. I would invite everybody in Singapore, especially beggars, to come. Because it's for food for beggars. Okay. But then the system may not be able to recognize this as negative comment and allow it. Okay, because it's very hard for people to moderate, especially for those big restaurants. So you may have an automated filtering machine. Yeah. So this is also how you ask questions. Okay, that's for surveys. Okay, so they are structured to collect numerical data. Okay, what's the problem with collecting numerical data? Okay, sometimes when you collect numerical data, you feel that, wow, this is very scientific, this is very quantitative. But the people answer is 4455, 444, 3344, 555. They just anyhow fill up. Okay. Yeah. So sometimes what people do is they do this thing called reverse. So they have similar questions, especially for some tests. They face it, some question is positive, some question is negative, the other way around. So some question will cancel each other. So if anyhow answer, you'll know that it's unstable, because in some questions you answer 5, in some question answer 1. So it's not very stable. Yeah.
The experts are here, maybe you can ask them.
Oh shit, the expert, yeah, I don't know. Ask. Okay, what should I call this? Okay, maybe the expert can mention about your questionnaires. Actually, I forgot, yeah.
Mhm.
Do you all do questionnaire or do you do more surveys? Text open-ended surveys.
Yes. So if you know a lot about what that people will find it, you can form the assumptions for the
Can. Okay, sorry, I forgot. Actually, it's quantitative method. I should focus on quantitative. Okay, next is experiment. Experiment can be, for example, one patient I give this drug, another patient I don't give the drug. Then I record the blood pressure to see whether the drug works or not. This is in the sense of an experiment instead of a clinical trial. This is where you can test a hypothesis, or you say low salt diet, for example. So one group you give low salt, then you check blood pressure. Another group you encourage normal. We don't usually maybe this case not so bad, but usually we don't purposely make the person eat salt. Yeah, maybe animals can. So animal study, you can have a group of rats, low salt. Another group, you feed a lot of salt. And you check the blood pressure or something measurements. So these are ways you can compare the result. Finally, this is very common in our department, administrative data. Administrative data. But remember, administrative data, there are records recorded, not for your experiment, So please don't expect the best, like everything there, So it's only collected for the needs or recording. So a lot of times people say, hey, where's my BMI? Where's my BMI? No BMI. BMI is body mass index. So it's basically your weight divided by height squared. So it just need two things, the weight and height. But you realize in our database, right, a lot of weight and height are missing. Or worse still, there are people that is 0 kg. Okay. There are people with 200, 300 meters tall. Okay. So all these are the errors. So some system, right, a bit smarter. So what they do is they have certain minimum and maximum. So this is to minimize doctors or nurses to key in the wrong number. Because sometimes, especially for height, people like to key in cm, 168 cm, for example, instead of 1.68 meters. So some people just anyhow key because they just want key in. Yeah. So this will help to reject certain things. So when you do data cleaning, right? If you don't do data cleaning, remember when you do BMI, right? Please remove unreasonable BMI. Because there are people that are 0.1 meters tall. Not possible, 0.1 meters tall. That's 10 cm. Okay. So if you use that 0.1 meters tall, they have BMI of 200, 300. That is also not possible. I don't know what's the worst limit. I think worst limit for BMI is 100 something. Okay. So in a database, we have BMI of 5 or 1. Also not possible. So you need to have some idea of the extreme value. I think this is where your data science come in. We get inputs from the clinical people to know what are the values or BP, for example. Your blood pressure cannot be 1,100. If it's 1,100, it's most likely 110. And then the doctor put extra 0. You can't have a systolic blood pressure of 1,010. Okay, if you look at a database, I'm sure all you've seen before, 1110 data things. Or even better, BP is 11060. 11,060. You know why? Yes, because instead of putting diastolic and systolic, the doctor just put 11060 together in the systolic. So end up with 11060. So there are a lot of permutations for blood pressure. Okay. Yes.
Also, sometimes I suspect that in terms of the data collection, like for instance, BMI, sometimes it's blank, sometimes are not blank when it's not compulsory. And if we so-called don't consider anything and we kind of imputation, whatever, I mean, we may get biased data, correct me if I'm wrong, Dr. Gary. So for instance, the clinic may just want to record BMI for the factor patient.
Yeah.
And then you're not getting the so-called normal result. So even when data is totally empty, okay, data is good. But when data are partially filled, you also have to be careful that I mean in our terms is whether is it randomly missing, what do you call that? missing at random.
Missing at random,
things
missing
like that.
complete at random. Yeah. So this
Be
is the missing
careful to
data.
do with observation data.
Yes. Okay, and building data lah. Okay, so one thing that's almost always collected in the clinical record is drug allergy, because if you don't put in that, you cannot save. So for drug allergy study, I think you have almost 90% complete data, because in our EPI system, you don't fill in a drug allergy, you cannot save. But that's also a danger, because some doctors, after patient leave the room, start typing, right? Okay, any drug allergy? I never ask. Okay, so
NK.
So I either call the patient back and ask, or no known drug allergy. So there might be some systemic bias. That's what happened with smoking. So JCI is a quality accreditation. So in JCI, this quality accreditation, you must put your smoking status. So what happened is that the smoking status is very badly filled up. So what the NHGP, okay, sorry, what somebody did was they just put that you by default nobody had a smoker. If you're a smoker, you click you're a smoker. So in one stroke of thing, everybody now had a smoking status being accessed, which is non-smoking. Yeah. So the doctor just ask whether you're a smoker. If yeah, I put as you're a smoker. Otherwise, you're not a smoker, because the patient never tell the doctor that he's a smoker. So the doctor never record it down. Bias. Okay, so these are some of the things I'm careful. So be careful when you see data, especially for routine data. Okay.
So I suppose one way is that after you analyze something, it's good to check with certain, like maybe a survey done by ministry or whatever. Hey, then for instance, prevalence of smoking and all those things, whether does it gel or not? Yeah.
Okay, quality methods. This one is the SPOR expert. So interviews, you have in-depth discussion. So interview is usually one-to-one. Okay, so you have somebody asking. So you can have a structured interview. So there are certain questions that you cover, okay, fully unstructured, but then you may get mixed up.
Why not you ask Mary and Sherlyn to cover this?
Okay, I can cover. Want to cover this? Qualitative methods, focus group, observation study. Anything else?
Okay, so practically speaking, it's about 30 minutes to 60 minutes for practice. Focus group, seldom have. I mean, it's common enough, but I seldom use it. The main point to remember about focus group is the interaction amongst the participants. Otherwise, it becomes a group interview. Like, I'm just gonna ask one question, everybody go round robin answering the question, then you get different answers, right? But in focus group, we want them to interact so that we are looking for rich data, not so much quantitative, but rich. Observations, you just observe in a naturalistic environment, how the person will behave without you around. He's just gonna, like MDRs, right? They're just gonna talk what they're gonna talk about the patients anyway with or without you. So all the number one and number two usually combined, we have what we call ethnographic studies. We should take some time. So observational studies can take months so that you understand the culture of the practice. In hospitals, we do this thing called focused ethnography. So you're very, it's very bounded in time and practice, and looking for like specific things, specific practices or like communication patterns.
Okay. So just one small little thing for observational studies, sometimes for children, because it's not ethically correct to intervene on children, not like in the past. In the past, they used to do a lot of things to children, which is no longer allowed in ethics. So a lot of times you can only do observation study. You cannot intervene. No. You're very careful. Yeah. So that's why observation study, not just say it's only for children, but for children specifically, you must make sure you don't interfere with the growing up. So last time there are studies to say that I give you a sweet, then I give you a cane you, all these things. It's no longer able to done because of activity, because it may affect the growth. That's why all these things are in a different era. So if you're interested, you can look at child development theory and how it used to be able to do a lot of things, like twin study, for example. One twin in one family, one twin in another family, and so on. Okay. So that's a little bit about that. Very good, Mary, that show everything that I don't know. Yeah, so thank you so much. Okay, so that's what we learn from each other. Okay, next one about descriptive. Descriptive is something that is the basic, you must know this very well. Okay, so basically is to make sense of the data. They always say what is mean by that. So usually what I need to do is look at the, for example, you know, difference between mean, median, and mode. I think mathematics you all should know, right? Okay, so for mean, do you know how many types of mean are there? There's arithmetic mean, there's geometric mean, and there's a harmonic mean. Okay, okay. So this is very interesting. Okay, so coming back to investment. So for investment, right? I asked my professor, which mean should I use? Arithmetic mean or geometric mean? Another professor in economics said you should use arithmetic mean because it's simpler. Yeah, I didn't like the answer. Okay, sorry, I didn't like the answer. But this finance professor could give it an answer. The arithmetic mean is the unbiased estimate for any 1 year. That's why you use the arithmetic mean. If you use geometric mean, it depends on your base year. So your base year is very low, very poor. Your geometric mean will be higher. And therefore, it's a bias. Depends on which year you use. So I find the answer was one of the best answer I had. Maybe that's for my MBA. So that the professor was giving a very good answer. Harmonic mean is a combination of both. I don't want to exact detail. You can Google what's harmonic mean. Okay? And Google search. So my point is that something simple, right? It's not so simple. When to use arithmetic mean, when to use geometric mean, and when to use harmonic mean. Okay, so think about it. Okay, median quite straightforward, right? So ranking lah. Okay, so rank it, find the middle, and if it's even, is it or odd? If it's even, you must add 1 divided by 2. Can't remember already. Okay, so if it's even, you divide by 2, then take the middle. Yeah. Then odd, then just plus 1 divided by 2, is it? Okay, whatever. So medium is the middle lah. Okay, with the data don't have to do. Last time I had to do manually, do the ranking. Remember primary school, secondary school. Okay, most common, most people don't use mode, don't know why. But then you have this thing called bimodal. So mode by itself is not so useful, but sometimes you have bimodal model, means there are two slightly high point to show that, like for example, I think certain phenomenon is two bimodal. I think height is probably bimodal. Was it normal?
Nope.
Then what is bimodal?
ED arrival rates.
Okay, maybe.
Time
So height is a normal distribution, then some that is bimodal. Okay. If you take an observation of patients' data, you can also get bimodal. One on treatment, one not on treatment. You can see the distribution. Then you realize that actually, is this one population or two population? Yeah, so these are something to think about. Okay. Then frequency distribution, I think, who was it talk about the waterfall graphs? Yeah, so we can show all these things, the distribution, the things. Okay, all these things you are expert. I don't need to talk about all this. Okay, so I think the last time we have a boss, she also don't show bar chart. No, don't show pie chart. Okay. What y'all think? Should you show pie chart? Or you're experts in visualization? Pie chart? Don't show or show, or I don't care. Pie chart. Somebody said don't use pie chart because it's not very useful. So anyway, so these are some of the things. Okay, these are don't go too much. This one is more interesting, it's more analytical. Okay, this is the next step. So descriptive is so simple. You can put the data into Tableau, put the data somewhere, and they'll give you all these things. So here in HSOR or DSOR, we need to focus on at least something a bit higher. That's analytical. That's my level. I can do a bit of hypothesis testing, and then test whether p-value is less than, you know what's p-value, right? Oh, you know, right? So p-value is a 95% confidence interval of a certain thing, so that if it's less than that, you cannot reject the hypothesis. If it's more than that, you can reject hypothesis. That is different. So there are different ways to test it. It's not so straightforward. There's even this thing called whether there is a difference in if non-inferiority trials. So there are different ways you can test a hypothesis. You can test whether it's a proportion or mean and so on. Confidence interval, usually use 95% confidence interval and see whether they cross. Regression analysis is a basic one. There's a simple regression. Then there's a, okay, I think I don't need to talk about this. Okay. You are expert in this. Okay. Or you want to go through? Don't need, right? The next one. Okay, after. Oh, you want, sorry. Okay, so which one you want to know about? So hypothesis testing. So for example, you have one population here, another population here. The usual one is, are the population the same? Okay, so for example, you look at the mean, you can test the population A and population B. So a hypothesis that there's no difference in them. Okay, that's a hypothesis. That's your H0. So H1, the hypothesis to reject is that there is a difference. So when you do compare the mean, for example, you found that they differ significantly. Okay, using, I think for me, you can use t-test, and then you can compare, and you found that one population is lower than the other by a significant amount, and therefore you will reject the hypothesis, and therefore there is a difference. So when you see that P is less than 0.05, you say that the two groups are differing in some characteristics because it's easier to disprove than to prove in mathematics. So here your theory, your hypothesis is there's no difference. Okay, then you test, hey, not correct, reject. If you reject there's no difference, means there's a difference. Okay, so that's hypothesis testing. Okay, so here in epidemiology, sometimes we don't really talk about p-value because it's not so easy to interpret. So nowadays we talk more about confidence interval. Does a confidence interval shift? Okay, even for p-value, if you talk about multiple testing, you need to take I think was it Cheryl or somebody mentioned you need to do a correction. I think it's called bonoforic correction to adjust for multiple testing. Okay, you can go and Google it. Okay, so then your p-value may need to set a lower rate, 0.001 rather than 0.05. Yeah, to account for multiple testing. Then regression analysis is just, okay, so regression analysis is to correlate two values and see the relationship. Okay, so regression, usually you have a few types. You have linear regression and you have logistic regression. The simple linear regression is to predict a certain numerical value. For example, you can regress income with age. So you regress income with age, you usually will have this curve flat. Nobody has income at this age group. Then as you grow older, there's an income rise. And then as you reach a certain stage, you start to stagnate and then start to decline or drop to zero. So this is a regression of income with age. Not correct, man? Okay, so this is income with age. Then logistic regression is looking at yes, no, for example. So for example, diabetes. So again, for diabetes, initially for age, there's an increase because of type 1 diabetes. Then after that, you no more type 1 already, so it's flat. Then as you go older, 40 years, you start to go higher again. So that's a regression. So your chance of getting diabetes is a bit higher for the younger age group, that's type 1. And then for the older age group, as you grow older, your risk get very high. Yeah. And then after that, you plateau off maybe at about 70, 80. You know why?
Then people die.
That's one way. What other things? When you grow older, your diabetes rate drop.
Oh, because diabetic people die.
You have those with diabetes or die. Yeah. One answer is very simple. When you reach 85 years old, 90 years old, even you got diabetes, no doctor will test you. So you're not tested, you never get diabetes, even you have diabetes. Because the screening age group, usually at a certain age group, the screening rate start dropping. First, you reach a certain age, right? You're already 85 years old. Even you got diabetes, we're not going to do much to you because you're so old. You may die from all the medication given to you. Yeah. So a lot of times, we don't really actively test. That's why you can see a drop. So always remember, when you see diagnosed rate, right? Is it real or not? Or is it they're not tested? For example, SAF, you see a huge increase in hyperlipidemia in SAF. Why? Because before enlistment, they tested. Normal population don't test. Then you can say, hey, go STF means you got high risk of hyperlipidemia. So don't draw a wrong causality. It's because you go there, you are tested. That's why you got this peak. Yeah, and that's the reason why. Even for that, even for a lot of conditions, at 40, you start to shoot up. Why? National screening guidelines start at 40 for most conditions. So 40 start to increase. So it may not be real. Yeah, if you do a study, unless you monitor people throughout their life, if not, you see this sudden jump. Or sometimes it's because of certain policy, then you can see sudden increases. Yeah.
Also for our data, our admin data, we have this data point called onset data. You think have gone using, and you find that hypertension, lipids, and diabetes all happen on the same day because you do blood tests on the same day, the result come on the same day. So it doesn't mean that the sequence of the diseases are on the same. So
yeah, thank you. So that's analytical. Okay, move on. Predictive. Okay, this one is a bit beyond me because I do some, but I'm not an expert in this.
you want them to take over?
So you all should know machine learning model, time series forecasting. Anyone do time series here?
Ask them.
Then there's ARIMA, all these things, right? I only cut all I didn't really do actively. I think Sui is very good at that. For those interested in finance, you can do some sort of regression to predict stock prices. Okay, that's my area of interest. Okay, and then risk assessment model. Okay, risk assess. I think all this we all do. I think most of the time, okay, key thing is use historical data. And as you know, sometimes there's intervention, and because of that, that can cause your model to become inaccurate. That's why you need to do some sort of adjustment or some sort of it's called data drift. Maybe the three legal scientists, data scientists, we should add predictive. Anything? Nothing.
This historical data
Yes.
is not retrospective, right?
It should be historical data means at this point want to build a model is historical.
So it's the kind of
It has to be retrospective because you can't use future data to predict.
Get it?
Yeah.
Okay.
Yeah, so it's past data. So correct. So you have to use historical data or current data. But they always say this thing, history does not predict the future. History does not predict the future. But when you do all these models, it's always predict the future. Yeah. So it's actually, it doesn't predict the future, but it's probably the best guide because no other way can you forecast the future. Yeah. So history is probably the best way for you to kind of have an educated guess. Yeah. So must be very careful when you do this. For example, if you look at the previous 2 years or 3 years data, you see a COVID cases. So if you use that as an extrapolation, Singapore will still be in crisis with insufficient bed due to COVID. Yeah, so you must think of changes. So you cannot rely on the too long ago data because things change. Yeah, COVID cases improve and then drop off. So don't extrapolate. Yeah, same as companies. So sometimes some company you can see that they have a 20% or 50% increase in revenue. It's not possible to increase your revenue by 50% every year for 10 years, 50 years, 100 years. Otherwise, you'll be bigger than the entire economy. So don't extrapolate to the trees. This is what they call. So even if the numbers, you see that our patient number is doubling. I tell you, unless you increase the number of beds, there will be a time when this number will suddenly drop. And you say you've done a good job, you stop the doubling. Actually, no, because our capacity cannot increase to meet the demand. Okay, so all this fear mongering, okay, there'll always be a cap. Okay, especially for those high rates, 10, 20, 30% rates are usually actually not sustainable. There's this thing called rule of 72. Anyone heard of rule of 72? You take 72 divided by the growth rate, this will give you a number of years, it will double. So if it is growing at 12% a year, 72 divided by 12 is 6. So 6 years, it will double a number. Yeah. Okay.
So what's machine learning?
Okay, machine learning. Okay, that's a good question. So there are different models you can put into the computer to kind of do the thing. So even linear regression is considered a machine learning. So other things will be like random forest. Okay, why? Not correct. Yours say.
I mean, if machine learning, if it's correctly linear, then machine learning will be able to spit out the linear.
Okay.
Yeah.
What?
So technically, is
So what other models are?
sometimes it's not linear. Then that's where the machine learning comes in to try to fit. Yeah.
Try to get as close the natural trend. Yeah, but it's not all the time. Most of the time it's very close.
Some other functions yeah. Okay. Neural network is machine learning, right?
Yes.
Okay, so there are neural networks. Yeah, I know some neural network. I did that. Okay.
So quite interesting is machine learning. Last time they use neural network. Last time was one layer, so it's just one layer of neuron. So that's linear. Then they realized it wasn't very good. Yeah. So then later on they say, oh, how about we add another layer? Then it is able to like model non-linear behaviors. So the way they add non-linear is like a few ways. So this is too technical.
But the problem with a lot of this model is it's a black box, not easy
Yeah, it's a black
explainable.
box.
But the usual traditional statistics is easier to remember, to understand which variables, what is the proportion. Because once you use the neural network, it predicts very well. But then it doesn't give you what is the contribution that easily. Of course, there are ways to see which variables factor more, but you have to work do more. Okay, but this is not a course on machine learning, so we will not talk so much about that. It's not expertise also. Yeah, I did advanced machine learning in business analytics. Okay. Okay. So this one is the prescriptive. So from that, there's actually one more. It's called cognitive. I didn't include it because some people disagree with that. Okay, so prescriptive is, okay, so first you describe, you analyze, then you predict. After that, so what? So one of the things that we talk about, like Chun Wei, he talked about there's this predictive model for readmission rates, for example, readmission. right? Who will be readmitted? Then what? You need to have prescriptive. What are you going to do next? Okay, so based on the data, based on the predictive modeling, how do I optimize resources? That is his expert because he's OR operation research optimization. Again, on my expertise. Then you can have decision tree, how to decide, and you have simulation model. You can have micro simulation, again, on my expertise. So I just give a brief thing. Yeah, do you want to talk about?
I think I don't know what you define by decision trees. I mean, decision trees, there are two. One is in terms of the machine learning method,
Machine learning.
whereby you do the fitting and all these things. So to that, I still consider that as a prediction. But of course, if you go to the decision analysis part, then of course,
Decision making.
I mean, for prescriptive, we talk about decision making. So that among all the options, I mean, the simplest examples that we can get is that from point A to point B, which is the best route? I mean, which is the best thing that you want to buy? So there's always the concept of best and what to do. So it's prescriptive. It's not just predictive. Predictive is what is likely to happen. Who are the patients who are likely to have diabetes? But there's no kind of actions involved, decisions and actions involved. So that's our definition of prescriptive. So under this, I would say simulation models is also not a prescriptive model. That's my definition. Because simulation model, by the name of simulation, it just means that simulate what will happen. How will the crowd move? How will the weather be like? But it doesn't give you an answer. So for the prescriptive models that we talk about is that, okay, tell me where to place the next hospitals such that you will cover the patients most, something like that. So tell me where. So this is what we define as prescriptive models.
Okay, maybe
Machine learning can also do
Examples?
reinforcement learning
But the purpose of reinforcement learning is to
predict.
to
more precise. Examples? Okay, what happens inside machine learning models, I would say, is that it builds the idea of reducing the errors as the objective functions. Right? You want to minimize the errors by training the parameters inside. Inbuilt the concept of optimizations inside that, reduce the errors, right? But after that, when the model itself is to do a prediction, right? In your machine learning models, right? So it's still a prediction, right? Unless you give me more examples.
like chess playing machine.
Okay, chess playing in a way it is, but okay, so that's a machine learning, but underlying the machine learning algorithms is what?
Is some kind of decision tree.
Possible, but it is slightly off from the say a neural, slightly off like, but yes. Okay, for that, then there's a purpose. The purpose is to improve the probability of winning, something like that. So then there's an objective. So it becomes prescriptive. Tell me what is the next move is. Yeah, that I agree.
Okay, thank you. So I think this is more about using the methods for you to make decision or action. Okay, so I think move on. One more thing is called cognitive. Cognitive, some people talk about it. Cognitive is to simulate the human decision making. But it's not a term that is fully accepted, so I didn't include here. Okay, this one I think a lot of people have seen it before. I think I asked last week, you remember? So those who remember, don't answer. What does this show? Yeah, the story is very simple. So this shows, these are actually planes, right? That return to the base. Okay, so these are planes that were shot down. Sorry, mistake.
These are the planes that return to the base.
No, don't shot. Okay. See, you keep confusing me. Okay, these are the planes that return to the base. Okay, so based on the planes that return to the base, so you look at this and say that let's reinforce those bullet area, because these areas so many bullet holes, right? So this is the quick level 1 thinking. We see a lot of holes with a lot of red dots. Let's reinforce this area. Is it correct or wrong? Those who don't answer, please don't say. I repeat again. These are planes that came back to the base, and then they found that there are a lot of bullet holes, red bullet holes.
In the context in the war
environment, so they come back.
A lot of aircraft go, and then these are aircraft that come back.
And they say that, okay, I realize all these planes, there's a lot of holes in the area. Okay, let's reinforce this area so that if they get hit, they will survive. Is it correct interpretation? Why not? Okay, possible. random, but you can see there are some areas, right? This is here and this is here. So you can see the wings are being hit, the center and the end. So like there are some parts that are not being hit, right? Any other idea for those who don't know the answer? Okay, so this idea looks possible, right? Because you just jump in and say, okay, these are areas, but you didn't think deeply enough. Remember survival bias? These are places that came back. So came back. Came back means I get hit by this area, I still came back. Okay. How come I don't have any plane that will hit at this area
The propellers.
and this area and this area? How come? If you mention it's random, you should see randomly, right? But you realize that, okay, so somebody say, why not? We look at, maybe another explanation is that those planes which got hit by the white areas never come back. So they crash. Okay, so when you look at epidemiology, right, you must always think of this interpretation, very important, okay? Are you trying to reinforce areas that are being hit and are being survived? Or should you focus on this area when nobody came back? Okay, when reinforced. This is very important because of disease thing. So for example, you look at this give a simple example. Let's say your diabetes clinic. Okay, they see a lot of Chinese patients in your clinic. Okay, then you conclude the Chinese are high risk of diabetes. You should focus on the Chinese. Is it right or wrong? Definitely wrong, because Chinese is already 70% of population in Singapore. So you expect 70%, but you see that only 60% of the population will come to see you as Chinese. So actually, although Chinese is 60%, right, it's bigger proportion, but you are in proportion to the general population, it's actually 75, 76%. So actually the biggest problem is the people who don't come to see you, or the minority races. Okay. So in actual fact, if you look at any study, right, for diabetes, right, although Chinese are the majority still, Malays and Indians are overly represented. That's the reason why a lot of intervention, you need to focus on the minority race. Or in some cases, you need to focus on people who don't come see you. Okay, so this is population health, focusing on people who are not seen, the unseen. Okay, the unseen people, not the crying baby who you see them all the time, but the unseen people. Okay, because they don't see you. Okay, just like a lot of patients, they die and they found that they have no diabetes prior to their death, but actually they could have, but undetected. Okay, so these are something to think of. Okay, so I think that's the end. 4 more minutes. So next week I'll go through descriptive epidemiology. So time, place, person, population at risk, and understanding time at risk. So this is what I'll cover. Okay, any question for this? And then I'll focus on week 3, which is disease frequency. You talk about incidence prevalence, more details, more example, how to calculate. Okay, and then summarize data and this thing called years of life loss. Okay, and it's equals to the I don't know what is it called, YTD and what, never mind. We'll cover that soon. Okay, then association and risk. So we cover some of this. So we talk about this attributable risk. I think it's too chim, so I will cover it slowly. Population attribution risk. The Hughes criteria will be here. So somebody asked about causality. Anyone know what is Hughes criteria? Offhand. Okay, you can Google it. So a lot of times when I go through this lecture, you don't expect to learn everything, because maybe 80% of what I say is true. The other 20% is not true or outdated. Okay. So you have to come up with this. As here, when you talk adult learning, right? You know a lot of things that different school of thoughts. People have different school of thoughts. So if people have different school of thoughts, so you must focus on what is fact and what is opinion. Okay. So facts I can give you, and opinion can also stray you. So you should also take an active and skeptical approach to whatever I say. Because what I say may not be fully correct. Okay. I try to use textbook. Yeah, so textbook, we'll go through the answers. Yeah. And then we'll talk about a bit about this one. This one important, all the different study design. Okay. And then the biases, they will cover bias. Don't scare you off. So the different type of biases. Okay. And then data collection again. Regarding how do you validate observation studies, techniques. Okay, what things they do. Live data analysis, clustered data. Okay, some of these I'll cover. That's it. Okay. And then we'll cover probably end of the year. Okay. Any questions? There are still 2 more minutes. Any feedback? So this is, remember, this is just okay, or anything you think I should cover but I didn't cover. Here we do, okay, this is going to be a very, I think I send you the slides. If not, I send you the slides. So this is going to be very, what's the word called? Interactive. So you want to cover something, or okay, maybe go down other than you. What problems or what epidemiology would you like to learn? Okay, can you just give me one. Maybe give me two things. What would you like to learn and what's the takeaway from today? Okay. If you got answer, can skip. What is it that you want to learn and what is the one takeaway from this today?
Today I learned fair bit from Mary. The qualitative things.
Okay,
I think
good.
that's something that we always need to be aware.
Yeah, 30 to 100 minutes, 30 to 60 minutes things.
Some of this ground
And
thing I mean on practice things like that, on theory and all these things you may not come across that easily.
We should invite Mary to give qualitative 1 hour on qualitative stuff. Really? Can? Okay,
I
good.
think 1 hour is like
There's someone lecture already. Okay, next. What is it you learn and what you want to learn?
How to say what I want to learn. I guess what I learned today is the different type of studies. Yeah, and I guess the basic concepts.
Are they new to you or you learned before? Or you forgot? Or
I come across before, but some of them not so precisely.
Okay.
Roughly I know.
yes.
What do you think about the other reasons why we choose such a
Don't jump to conclusion. Okay. I always do that.
I mean, I've heard when in course of work, I read about like, this course, this talk is good because you put them, you organize them, right? And then after the, like, the idea of data interpretation, don't just look at what you see, but what's omitted. That's also in qualitative.
Yes.
Yeah, the sample selection. Yeah, you really know the context of what's if I did the training.
Yeah.
Would be interested in seeing what
Okay, good. Okay, I'm not a qualitative person. I failed the exam for qualitative. Yeah. We do. Then after that, the final exam, they give me the quantitative, I pass. So I always ask myself, if they give me qualitative, will I pass? Okay, never mind. Okay.
Qualitative, you must tell them.
Okay. Okay, fair enough. Yeah.
I think I learned about the different studies. And I think it was good, even though I'm a data science person, but I never really categorized the analysis in this kind of 3 points. So I think it's good to actually show the differences. And I think for data interpretation, it very often overlooked. Yeah, and something that we need to keep in mind. Yeah, I think what I would like to learn is learning more about the actual studies, how to actually compare. That'll be interesting too.
Okay, I'll be more detailed. Don't worry, this is just intro, a favor.
What I learned today is same as him. Like I keep hearing about all the ways you can collect data, but I never actually categorize them. And also the perspective versus retrospective, all the things you have to keep in mind.
Yeah, thanks. So I'll give a more detail and more example, real life example, hopefully. So make it more, okay, the key thing about learning for adult learning is to make sure there's something that is your work. So you got any work problem, work solution, things you want to bring to here, it'll be very good for sharing. So everyone can bring their mind and share it. For example, for me, right, I want to do this study for many years, right? Don't have the capability to do it. Is look at the effect of high blood pressure drugs on patients. But high blood pressure drugs keep changing over time. So how do you model the time varying part? And how do you isolate all the different other variables, patient compliant, not compliant, aging, all this, and decide which drugs actually works best in the real world? Well, I think this is very impactful because even now there isn't any guidelines on the best drug to use. We have guidelines to say that if you got this condition, like for example, you got asthma, you don't take beta blocker. Why? Because it may cause you to have asthma attack. Okay. And then if you got, let's say, leg swelling, then you cannot take calcium channel blocker, but that can cause leg swelling and so on. So a lot of times our blood pressure treatment is very empirical. So we just choose one and see if got any side effect or based on cost or other things. And some of the blood pressure medicine can cause diabetes, like the beta blocker, or this is a study I done many years ago, that beta blockers can cause diabetes, but it's often a first line because it's very easy and cheap to use. A lot of GPs are using it, and we see that there's a lot of diabetes cases coming up. Maybe it's related, maybe it's not. But anyway, these are some of the things I want to do. So maybe some data science can help me do this when you have time, if it's interest. So we have a lot of data, we have rich data set, not other than diabetes, you can also look at, other than hypertension, you can look at diabetes as well. How do you best model effect of drugs in the real world? Because in a clinical study, you only take one drug, you cannot take another drug. You take another drug, you're out of study. Yeah, but in the real world, people switch drugs. How do you model that?
But that's the inherent issues with us, HSO, as in most of the time we only have administrative data. We hardly do prospective data collection. I mean,